For many outdoor ice rinks, like what you'd find in a park or someone's backyard, the water in the rink is slowly cooled by the outside air until it's frozen. However, if there's a few days in the middle of winter where the outside temperature gets really warm, the rink can melt. As climate change causes warmer temperatures and more extreme temperature swings, these midwinter thaws are more likely. The current solution for outdoor ice rinks is expensive refrigeration equipment designed to remove all the heat that goes into the rink on the hottest days. We set out to develop an alternative solution that could cost less and require less electricity to run. The key to our system is the addition of a phase-change thermal reservoir, a big insulated container of water with a little bit of antifreeze that takes advantage of a basic concept in thermodynamics. It's harder to send heat from the reservoir to a warm place than it is to send it to a cold place. Our thermal reservoir system freezes during the coldest parts of winter, and when the temperature outside is warm enough that the ice rink would otherwise start to melt, the antifreeze mixed into the water causes it to melt first. This steals the heat from the ice rink, keeping it frozen until temperatures drop again. To show you how the system works in detail, let's take a look at the most important parts. Here's the thermal reservoir. We've also got an ice rink over here with a bunch of metal pipes buried in the ice. A pump and pipes let coolant fluid flow between the thermal reservoir and the ice rink. We also have a liquid air heat exchanger, like the radiator that you'd find on a car, with pipes connecting it to the thermal reservoir. When the air first gets cold, the coolant fluid is pumped between the thermal reservoir and the heat exchanger, causing the temperature in the reservoir to drop. At the same time, the cold air causes the ice rink to freeze as normal. Once it gets cold enough that the ice rink is completely frozen, a valve is opened, and we use the ice rink itself as an additional heat exchanger to get the temperature of the thermal reservoir to drop as far as it can go. Once the thermal reservoir is almost as cold as the outside air and it's not getting any colder, everything shuts off to avoid wasting energy. If the air temperature rises enough to risk melting, the pump and valve connecting the thermal reservoir to the rink are turned on. The fluid circulating through these pipes causes the heat to go from the ice rink into the reservoir, keeping the rink frozen while the thermal reservoir's liquid melts. If the air temperature drops below zero again, the thermal reservoir can be refrozen, regenerating the system for use while keeping the ice rink usable. We've worked to refine our mathematical model of the thermodynamic system, including running tests to observe how much the temperature of ice changes as a response to air temperature. We've also working on using finite element software to simulate specific parts of the system in detail. We hope this will have a lifetime cost that's low enough for the ice rinks that cannot afford a conventional refrigeration system, while also having less of an environmental impact.